So we ended off on the last section doing Lewis dot diagrams. So we were looking in two-dimensional space. What happens when I covalently bond, either polar covalently or pure covalently, bond atoms within a molecule? So I have a question here. Why do carbon dioxide and dihydrogen monoxide have different shapes? They both have one central atom with two atoms around them, but they're very different. One of them is going to be linear, CO2 will be linear, and dihydrogen monoxide or water is going to be a bent shape. And the reason this is because of the VSEPR theory, VSEPR, which stands for valence shell electron pair repulsion. In general, what that means is that I have atoms, or around my central atom, I have electron pairs, and they are going to repel each other as far apart as possible. It predicts the most stable shape, and it orients electron clouds as far apart as possible to minimize repulsions. So to predict the shapes, the first thing we do is draw the Lewis structure, which is why we were doing that in the earlier set of our notes. Then what we're going to do is count the number of electron clouds, which is sometimes also called electron domains, that are surrounding the central atom. So some things that count as electron clouds, a single bond would count as an electron cloud. A multiple bond, which would mean a double bond or a triple bond, count as electron clouds. And an unbonded pair of electrons also counts as an electron cloud, or an electron domain. And then we start to predict the geometry of these atoms based on the number of electron clouds that they have. And we do that by orienting them as far apart as possible. And so those flashcards that we're having you make for this unit are going to become very important for you, because you'll want to memorize what these different shapes are and how we can predict them. So some of the ways we can predict them, we can look at the number of electron domains or electron clouds. If there are just two electron clouds, my shape is going to be linear. And this is my CO2 that I was talking about. So it has two double bonds, but nothing else around the central atom. We're not looking at these unbonded electrons that are around the oxygens. Those aren't the central atom. I'm just looking at the central atom and looking at the electron clouds around it. Here's one electron cloud. Here's the other electron cloud, or electron domains. Since there's only two of them, the easiest way to get them as far apart as possible is to be linear, at 180 degrees, as far apart as possible. Once I start getting 3 electron pairs, or I start adding electron pairs or electron domains, or electron clouds, then it starts to get a little bit different. So I could have 3 electron domains, and all 3 of them be bonds, so something bonded to something else. And an example of this one would be boron trifluoride, which, remember in the last notes we said was one of the exceptions to the octet rule. These fluorines each have an octet, but the boron does not. And that's because boron is so small that if we started fitting more bonds or more unpaired electrons around it, it would be unstable. So it's actually stable with 6 as opposed to 8. But it has just 1, 2, 3 electron clouds, and all 3 of those are bonds. So when that happens, it's called trigonal planar. I could have 3 electron clouds or 3 electron domains, but only 2 of them be bonded. And an example of that would be nitrogen dioxide, where I have an electron cloud that's a double bond, an electron cloud that's an unbonded pair, and an electron cloud that's a single bond. And so I've got 3 of those electron clouds, but only 1, 2 of them are bonded. And then I get a bent shape. Now we're going to see some other bent shapes, or V shapes, that are going to be a different angle than this, and that's because this one only has 1 electron cloud. Well, that's an unbonded electron pair. we're going to see some that have 2 electron clouds that are unbonded electron pairs. And those are going to push down more in 3-dimensional space the atoms that are bonded to them, and therefore it would be a smaller angle. So here we get to 4 electron pairs, and this is the maximum we'll go at this point. There are ones that go up to 6, but we're not going to deal with those according to our syllabus. So we have 4 electron pairs, or 4 electron clouds, and if we have all 4 of those being bonds, we have a tetrahedral shape. So we have a central atom with 1, 2, 3, 4 electron clouds, and all of those, 1, 2, 3, 4, are signal bonds. Tetrahedral is the name for it. And this is just showing us a 3D representation of it, where the dark triangle means that if I have, imagine we have this thing and we've got paper going through it, and so it's cutting it in half. In my paper cutting it in half, those 3 atoms, the ones that don't have weird bonds going to them, those are all within my paper, so that's in my 2-dimensional space. This is representing that it's coming out towards me, so it's coming out from my paper towards me. And then the dotted line represents it going behind the paper away from me. So this is a way to attempt to draw in 3D something that we only have on 2 dimensions because we're doing it on paper. So it's just a way of representing it. Okay, my next one, 4 electron clouds, but only 3 of them are bonds. So I have 1, 2, 3, 4 electron clouds, but 1, 2, 3 of them are bonds. One is an unbonded electron pair that's called trigonal pyramidal, or trigonal pyramid, depending on who you're asking. Our book refers more to trigonal pyramid. And so nitrogen trihydride or ammonia is an example of this, with that unbonded electron pair pushing those 3 hydrogens closer together. And then I have an option of 4 electron clouds, but only 2 of them being bonds. This is where we get our water. So remember, we had a nice linear shape for CO2 on this last slide. Here's water. This is why they don't look the same. And so we've got 4 electron clouds, but 2 of them are unbonded electron pairs. Those 2 unbonded electron pairs in 3 dimensions are going to be pushing those hydrogens closer and closer together, because those are going to be repelling each other even more. So here are some bond angles for us. This steric number just means how many electron clouds it has, so, or electron domains that it has, depending on which number we're looking at. So if we have a linear one, like our carbon dioxide, with 2 electron clouds, but and 2 of them being bonds, that would be linear. 180 degrees would be the furthest way to get them apart. Then we have trigonal planar. Trigonal planar is where we have 3 electron clouds and all 3 of them are bonded. That would be an angle of 120 degrees. Now when I have that 3 electron clouds but only 2 of them being bonds, we call that bent. Sometimes we call it angular, and that sometimes we also call it V-shaped, depending on where you're looking. That's going to be less than 120 degrees because that unbonded electron pair is going to push those bonds closer together. So that unbonded pair does more pushing than the electron clouds that are bonds. So it'll be less than 120 degrees. Now we've got our 4 electron clouds, and we had a couple of options for that. We had it where all 4 of them are bonds, tetrahedral. Those are 109, or actually 109.5 is a better way for you to memorize that, 109.5 degrees. If we have trigonal pyramid, so the 4 electron clouds but only 3 of them are bonds, it's going to be less than 109 degrees because that unbonded electron pair is pushing those closer together. And then finally, the 4 electron clouds but only 2 of them being bonds, like water, it's going to be much less than 109.5. because those two electron clouds are going to be pushing that together even more. And water is a bent shape, but it's a special one because those hydrogens are so small. They're sharing 2 electrons. There's nothing else around them. So their angle is actually one of the smallest that we're going to get, 104.5. So you can think of the regular bent or angular being somewhere between 109 and 104.5. So that's going to be my smallest one generally. We also can think of things as being either polar or nonpolar overall. We know that the bonds can be polar or nonpolar if they have electronegativity differences, but my overall molecules can be either polar or nonpolar as well, and that depends on the shape. So if I had here 2 of the same atoms, and that's why they're both listed as X, with my central atom being E, they would have an electronegativity difference, but since they're the same values, or the same atoms, their electronegativity differences are going to be the same. But they're going to be going in different directions. So if you can think of a number scale where this is 0, let's say this one is going up a 1, and that one's going down a 1, my net difference is 0. So my overall molecule here, even though it's got 2 bonds that are polar, my molecule is going to be nonpolar overall. The same sort of thing is happening with my trigonal planar. Even though these look odd, they're going to be nonpolar overall because they're going in kind of 3-dimensional space, and so they end up canceling each other out. Whenever I have an unbonded electron pair, then I'm going to have a polar molecule overall because I have that very negative section of the central atom. So even if those were to get close to canceling each other out, they're not going to because of that unbonded one. So a bent molecule is always going to be polar. Tetrahedral, as long as those 4 elements or atoms on the outside are the same, they're going to be nonpolar because in 3-dimensional space they end up canceling out on those scales. Then we have trigonal pyramid. Again, I see unbonded electron pairs, so that would be polar. And then I've got unbonded electron pairs on these bent ones as well, so that's polar. Again, all of these nonpolars are assuming that the X's are the same atom. If we were to get one of them being a different one, they're going to pull at a different rate than the other ones, and so those have the high likelihood of turning into polar molecules because they do not cancel out, because they're not the same atoms. So a nice flowchart is in your note packet that we can ask ourselves whether things are polar or nonpolar. So first, does the molecule contain a polar bond? If it doesn't, then we know it's going to be nonpolar, and an example would be our diatomic molecules. Or in ethane, there's not a significant difference. If yes, they contain polar bonds, we determine the shape of the molecule first, so that's where we do our Lewis diagram, and then we do our VSEPR shape rules. We'll determine the shape, and then we ask ourselves, are there polar covalent bonds arranged in space in a way that causes them to cancel out, like our tetrahedral or our linear? If so, then it would be nonpolar overall. If no, then it could be polar overall. And we have an example of methylene chloride here being polar because the chlorines are partially negative, the carbon's partially positive. Since it's not on all 4 atoms, they're not going to cancel each other out. Then we have what are called allotropes of carbon. So these are different forms of carbon that exist in the solid state, and some examples, are the main ones that we have, are diamond, graphene, and fullerenes. They all have a giant covalent structure, and giant covalent structures have some important special properties, and there's a good bit for you to read in the textbook on that. Let's look at diamond. So diamond is where we have each carbon joined to 4 other carbons tetrahedrally, and we know that SiO2, silicon dioxide, behaves this way as well. And it doesn't matter the size, this is still just carbon. So I could have a really big diamond or a really small diamond, but it's all carbon, unless it has impurities in it, in which case it's not just diamond anymore. Like those chocolate diamonds that they're trying to sell now, those are just carbons that have impurities in them. Diamond has the highest melting point of any element, and it's the most closely packed of all of the atoms. We also have graphite, which is made of graphene, and these are held together by two things. The atoms within the 2D shapes are held together with covalent bonds, but between sheets of them, they're held together with London dispersion forces. So the London dispersion forces hold two-dimensional groups of carbon together. Even though they say diamonds are forever, it's actually graphite that is forever. Graphite is a much more stable form of carbon, and it's going to stay graphite forever. Our diamonds that they say last forever, they will start degrading into graphite over millions and millions of years, but they will degrade because it is a much more stable structure in graphene than it is in diamond. They're made up of a 6-carbon ring that is as the most basic part of the structure, and we see that here, 1, 2, 3, 4, 5, 6, and those are held together. All together, it looks kind of like a honeycomb. And then we have the fullerenes, and there's a few different fullerenes in this image here. We have C60, which is called Buckminster fullerene. That was the first of the fullerenes that was discovered. We have C540, that's this one right here, and then C70. This one looks just like a soccer ball. So if you're a soccer player, every time you look at it, you should think Buckminster fullerene, where each of these dots represent where carbons are being held. And it's named after the architect of the geodesic dome. And the uses for it are in diagnostic tools, drug delivery, superconductors, and catalysts, to name a few. We also have, based off of the research that was done with fullerenes, single-walled carbon nanotubes, or they're called Bucky Tubes, like Buckminster fullerene. Okay, we'll take off the buck part, make it Bucky, and it sounds cute. So Bucky Tubes, they're approximately 1 nanometer thick in diameter, so they're really teeny tiny. They're 1 atom thick layer of graphene wrapped seamlessly into a cylinder. So this is really, really small. We've got just 1 carbon here bonded to 3 other carbons in a grouping of 6, and those are just 1 layer thick. Some properties: it's got extraordinary tensile strength, so we can pull and bend it to great degrees before it'll break. It has a range of electrical capabilities, and it's an efficient thermal conductor. And so it has great applications in optics, electronics, and in other materials. And we're not going to do these practice problems right now, but if you get a chance to, it's always good to keep practicing those Lewis diagrams and the VSEPR shapes.